yesterday we started talking about curve sketching, but we November 19, 2008. So yesterday we started talking about curve sketching, but we didn't do any of it, and we may not do a lot of it today. But what we are doing is recalling and then eventually building up all the tools that we're going to use to get the data, right? We're basically going to be data collectors. And then after we collect all the data, we're going to be forensic scientists, and we're going to piece it all together and then get our graphing done. All right. So, well, let's see. We had this expression that we can remember. It starts with die said, and then what does die say? Well, first a critical test. Then a cavity. And then a second test. Okay. Okay, so this encapsulates everything that to do. And yesterday, right, we covered the D, which was what? Domain, and the I? Intercepts. S? Symmetry. And then we started A, which is going to stand for asymptote. Excellent. Okay, so we'll talk more about asymptotes. And then we're going to do the increasing, decreasing test. And then perhaps, if we have time, the first derivative test, right, along with critical numbers. Okay, so we're just going to keep on building up more and more ways of collecting data. Okay, so let's go back to asymptotes. Remember, there were actually going to be a couple different kinds of asymptotes. And the first one, we're going to be horizontal asymptotes. All right, so we define two different horizontal asymptotes. All right, a left horizontal asymptote and a right horizontal asymptote. Okay, but they're really the same thing, just one goes to minus infinity and one goes to plus infinity. So a function f has a, let's see, we'll write left, right, respectively right, horizontal asymptote, if the limit as x goes to minus infinity, or for right, respectively infinity, of f of x equals L, for some real number L. Okay, so the functional version of this sentence is to say, if you want to find out if and what the horizontal asymptotes are, you compute the limit as x goes to minus infinity and x goes to infinity of f of x. And if you actually get out a number in either of those cases, then you know you're going to have either a left or a right horizontal asymptote. Okay. Notice I don't underline the left or the right because this is non-standard terminology. You won't find that in the textbooks. Okay, I just think it is nice to differentiate between the two and to recognize if you have a horizontal asymptote, that only refers to one side of the graph, right? It doesn't, if I, for instance, think of e to the x. You have a horizontal asymptote on the left, right? It goes to 0 as x goes to minus infinity, right? But as you go to the right, well, this thing, there is no horizontal asymptote. It goes up to infinity. Okay, so I would say this has a left horizontal asymptote. But in general, you would just say e to the x has a horizontal asymptote, y equals 0. So another way that people refer to the horizontal asymptote is by giving the equation of the line, y equals L. Okay? Okay, so these are the horizontal asymptotes. And we have a lot of experience, right, with taking these limits as x goes to minus or positive infinity, okay, of any function. So an example that we worked before, or close to one, if we let f of x equal, say, 2x cubed minus 4x squared plus 1 over 3x cubed minus 5x minus 6. You ask, what are the left and right horizontal asymptotes, if they even exist? Okay, and, well, this tells you exactly what to do. Compute the limits. Right, what's the limit as x goes to minus infinity? So where's the argument come from? Right? Sure, right? You can, well, a couple ways you can do it. One, if you tried plugging in larger and larger numbers, these things are both going to go to infinity, right? Or if you put in minus infinity, these things are both going to go to minus infinity. So you could use L'Hopital's rule if you wanted to. Right? You just start taking derivatives. Or you could factor out an x cubed from the top and the bottom, right? So you could write this as x cubed times 2 minus 4 over x plus 1 over x squared, sorry, over x cubed, over x cubed times 3 minus 5 over x squared minus 6 over x cubed. And as x goes to minus infinity, okay, all these terms with x's on the bottom, they go to 0, right? Okay, so those go away. You're left with a 2/3. Okay? And then over here, what happens to these x cubes? Well, we can cancel them, right? At least when x is non-zero, but as x is going to minus infinity, you're not worried about 0 anymore. Okay, so you're just getting 2/3. Okay, so that's good, right? We now know we have a left horizontal asymptote of 2/3. Okay, what's the right horizontal asymptote? Notice we nowhere in the argument did we actually use it. We were going to minus infinity, right? The fact we were going to infinity was relevant, right, in some direction, but minus never actually showed up. Right? All these things went to 0, and these things canceled out before you got to even plug anything in. Right? So you're going to get the exact same right horizontal asymptote. Okay? So this tells you that if you graph this function, right, whether you go left or right, eventually it's going to approach 2/3. Right? That is, gets arbitrarily close and stays arbitrarily close to 2/3. Okay. Any questions about horizontal asymptotes? Yeah.
So if it's equal for the left and the right, does that mean like on the left side of the y-axis, it's like, I don't, can you just like, how would that be like if you drew it graphically?
So what it's meaning, if we draw it. So remember, the horizontal asymptote only cares about long-run behavior. Okay? It only cares about what's happening as you go to plus or minus infinity. Okay? So all this stuff that happens in the middle, the horizontal asymptote doesn't care about. Okay? So without knowing what the graph of this looks like, we just say it does something in here, right? Who knows what it's doing in there? Okay, but now what you're interested in is what happens as you go out to minus infinity or plus.
So we're both going like this?
So that's a good question, right? Okay, so here, let's say this is the line y equals 2/3. And we know that it's going to be getting close to this line. Right? But we don't know from where it's coming without doing some more investigation. Right? we know that it could be getting close like this, it could be getting close like that.
Okay.
Could be doing all sorts, some weird things to get up there, right? And the same thing on this side. It could be going down, it could be going up, it could be doing some weird things. All we know is on both sides, and it doesn't have to be the same, right? It could be going down on this side to it, it could be going up on this side to it. You have to, that's where you have to do some more investigation.
What if the two limits aren't the same? The limit, the horizontal asymptote from the left and the horizontal asymptote on the right.
Asymptote.
Asymptote. Sorry.
Just think it should sound dirty.
Okay.
Okay. Good. So what happens if they're not the same? So you might be thinking, geez, when we talked about limits, right, you had two-sided limits, and if they weren't the same, then you said, the two one-sided limits, they're the same, but the limit doesn't exist, right? Okay, different problem here. Okay, we don't worry about whether they're the same, because instead of them meeting at the same point, one is going way over here, and one is going way over here. Okay, and there's no problem with that. You can have a graph that looks like, let's say over on this side, it's approaching that horizontal asymptote, and then coming down here, it approaches this asymptote. What do you think that is, by the way?
Cube? No. Cube is going to okay.
Is it cube root?
Could be. Could be. You have to think about it. Also might be a trig function that does that. Right? Kind of looks like, remember how tangent does this, going up and down, so this could be somehow related, possibly. Okay, so good questions, both. Yeah, so you can. That's why I differentiate, by the way, between a left and a right asymptote. You can really have different ones, right? And they give you different information. And strictly speaking, when people draw asymptotes, they usually draw these dotted lines. I'm sure you've seen that before. Okay, but if you have a right horizontal asymptote, which is different from the left horizontal asymptote, then it's almost a little misleading to put this line up here, right? Because nothing is going to be getting close to this line. Right? It only really becomes relevant over on the right side. Right? And the same thing with this bottom line. It's almost a little misleading putting it there. Okay? The reason why it's typically done is the horizontal asymptotes are written as lines. They say, okay, it's not just a number, it's really a line. Y equals 6, y equals 2/3, whatever it is. And so they draw in this line, right? Or at least they dot it to at least give you a guide. Okay, so let's try now to do vertical asymptotes, which again we've actually seen. We just didn't write it down precisely. Okay. So vertical asymptotes. Well, this is what is happening when you have, for instance, 1 over x. Okay, that's the example that you have in mind. Or ln of x. Okay, both at x equals 0. That's where you're having problems, right? With 1 over x, graph looks like this. In fact, you have something very nice. 1 over x has a lot of interesting things going on, right? You have a horizontal asymptote to the right and to the left, both 0. And you have this vertical asymptote at 0. Okay? Now, what does it mean that you have a vertical asymptote? Well, it should mean that the graph is going up to infinity or down to minus infinity. Okay. How do we write that? Say that f has a vertical asymptote at x equals a if the limit as x goes to a of f of x is equal to plus or minus infinity. Okay, but now this is not quite right. Okay, what's wrong with this? Well, when I say plus or minus, I mean one of the two. Okay, not both at the same time. Okay. But look at it, 1 over x. Okay. Here our problem point is 0. And as x goes to 0, the limit, what's the limit as x goes to 0?
Two separate limits.
But if I just say the limit as x goes to 0, what's the answer? It doesn't exist, right? Because the left-sided limit is minus infinity, and the right-sided limit is positive infinity. Okay? So if I just write it like this, I'm not going to get, I mean, the canonical case that I want to get at. So what do I need to do? Well, I need to put in the different directions. Okay? So I'm going to say that it has a vertical asymptote at this point if from either side you have a vertical asymptote. Now, this allows us to come up with some weird function that has a vertical asymptote at 0, for instance, and is yet still defined at 0. So for example, define f of x as 1 over x when x is less than 0, and define it to be the line x when x is greater than or equal to 0. Perfectly legitimate piecewise defined function. If I graph this, okay, well when x is less than 0, I'm on this side, it looks like that. And it's going down, 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 down. But at 0, it actually becomes the line y equals x. So this has a vertical asymptote at 0, and it's defined at 0. Okay, so this is a little strange, right? Normally you think that you have vertical asymptote, it better not be defined there. Right? But this one has both. Right? And that's because we allowed ourselves to look at the one-sided limits. Okay? And you only need one of them to go to plus or minus infinity to say that it has a vertical asymptote. And if both of them go to plus or minus infinity, it's fine. It still has a vertical asymptote, and they don't even have to go to the same plus or minus infinity. Yeah? This one goes to plus, this one goes to minus. Okay? To have a vertical asymptote, okay, you only need to check that one of these two is whole. Now, it's better for you to check both directions. Why? Well, if you don't, then you're going to miss out. Right? Although in this case, with 1 over x, I claim you only have to check the positive side to know what's happening on the negative side. And why is that? Well, what did we do right before we did asymptotes? It's symmetry. What kind of a function is 1 over x? It's an odd function, right? What does odd function mean? It means that if you take the graph on the positive side, flip it down. Well, that's exactly what you get. Flip it over, flip it down. You're going to get if you ever have a vertical asymptote at 0 going to infinity, and it's an odd function, well, when you flip it over and down, it's going to become a vertical asymptote going to minus infinity on the other side. So if you just know this about 1 over x, you can get this just by symmetry. Right? You don't have to remember how to graph the whole thing. Okay, so we've also seen examples where it goes to 0 in the denominator, and you don't get a vertical asymptote. So for instance, if we look at the limit as x goes to 3 from, well, we'll say the plus side to be consistent, and you have, say, x squared minus 9 over x minus 3. Right? If you plug a 3 into this equation to try to do things, right? We get 9 minus 9, that's 0. 3 minus 3, that's 0. 0 over 0, you can't do it, right? Okay, but then you note, oh, wait a second. This is just, right? That's x minus 3 times x plus 3. The x minus 3's cancel, so this is just x plus 3, and so I get 6. And then you notice, this plus here was irrelevant. Okay, fine, good. Okay. But it doesn't go to plus or minus infinity. So it doesn't have a vertical asymptote at 3, even though it's not defined at 3. Okay, and of course, ln of x has a problem at 0, right? It goes to minus infinity, so it has a vertical asymptote. Again, ln of x gives you a good reason why you can't just put in the limit as x goes to a without reference to a direction, right? Because ln of x isn't even defined on the other side of 0. Right? So you really need to just look at one of the directions. Okay, so those are the horizontal and vertical asymptotes. Go through quickly. Let me just quickly mention this last kind of asymptote I was telling you about, called a slant asymptote. And sometimes this is a useful piece of information, sometimes not. I'll try to do it as generally as possible. Let's look at this by way of an example. Okay, let's go x goes to infinity. Of course, everything will work on minus infinity as well. And let's write down a reasonable function, 2x cubed plus 3x squared minus 2x plus 4 over x squared minus 3x minus 3. Okay, what's the limit?
Infinity.
Infinity. Does it have a horizontal asymptote? Does it have a vertical asymptote? Well, let's see. Vertical asymptote is always at a point. Okay? A here is not infinity. Okay, so it doesn't have a horizontal asymptote because it goes to infinity. It doesn't go to a number, right? You can tell that because the degree on the top is higher than the degree on the bottom. Right? So you know it's going to infinity. Okay, so you might think, so wait, we get no information. This is horrible, right? Useless. Okay. But let's pretend we were trying to do this in a test. So we're going to write down all our steps. So we say, okay, let's factor out our x cubed on the top. Right? And we get our 2 plus 3 over x minus 2 over x squared plus 4 over x cubed. And then on the bottom, if we factor it out, an x squared, we would get 1 minus 3 over x minus 3 over x squared. Okay? And then we would cancel 2 of the x's. And we would note that as x goes to infinity, all these nasty terms with x's on the bottoms go to 0. Okay? And so you'd get 2 times x. Remember, we've killed 2 of the x's, and there'd be nothing on the bottom of 1. Okay, so you get 2x over 1. So this is actually equal to the limit as x goes to infinity of 2x. Which means that as x goes to infinity, this function starts to look like the function 2x. So it was one thing to say, well, this goes to infinity, right? So it's going off. But there's a lot of ways you can go off to infinity. You can go up really slowly, you can go up really quickly, right? Exponentially, polynomially, whatever. Okay, a lot of different ways of going up. This tells you it actually looks like 2x. So if you went to draw this, right? If you draw the line y equals 2x, you may not know what the function is doing around 0, but as it goes off to infinity, it's going to get closer to that line. It's going to start to look like that line. So you might be able to guess why they call this a slant asymptote from the picture. Okay, but there's nothing that actually stops you from doing this, right, when it's not a linear term in the end. Okay, this could just be some function. Okay, so this could be a quadratic, it could be a cubic, right? And that just tells you, well, as it goes to infinity, it starts to look like that cubic, right, or that quadratic. Okay, so sometimes this can be helpful for long enough behavior. But, you know, we don't use this so much unless we really have to. Yeah?
So how come you know that it's not a vertical asymptote?
Dirty one.
Asymptote. How come you don't know it's a vertical asymptote? Because it goes, the limit of that is infinity, right?
Oh, yeah. So why isn't this a vertical asymptote? The key, right, is what I'm putting down here. A vertical asymptote is only occurring at a real point, okay? Not when we go to infinity.
And the horizontal is equal to point, a value.
Yeah, horizontal is when you're going to infinity. Vertical is at a point.
Okay, and this one is not horizontal because...
Well, this one's not horizontal because the limit, right, is infinity.
Okay, if it's like 2 over 3 or something.
Yeah. So if this went to 2/3, right, or 2, if this was an x squared, then the limit would be 2. Then it would have a horizontal asymptote. So basically, the horizontal and vertical they switch places, right? With a horizontal, you go to infinity and you get a real number limit. With a vertical asymptote, you go to a number and your limit should be infinite. Right? So they swap the rules. Okay, so these are the asymptotes. Any more excellent questions about asymptotes? I won't hold you to that standard. Any crappy questions about asymptotes? Okay. It's fitting that you could have a crappy question about an asymptote. Okay, so that takes care of die set. So now we get to the id. So this really could be written with a little line in it. This ID should be I/D, right? And this is going to be for increasing, decreasing. Okay, and it's just a question. Where is the function increasing? Where is the function decreasing? Okay, so let's say somebody asked you, what does it mean for a function to be increasing? What would you say?
The second derivative is positive.
Increasing. The slope is...
Let's do it naively. As naively as possible. Okay? It's going up. Okay, this is a very good answer. Right? It's going up. Okay, so now somebody says, okay, what does it mean to go up?
Increasing.
Function be positive.
What does it mean for a function to be positive?
F of x is positive.
Okay, so
F prime is x.
this function is certainly going up, right? But it's always negative.
The difference between y values are increased or positive.
Okay, we're getting a better idea, right? Something about the y values, right? The y values are going up as what? As what do you mean by the line progresses? As the x values go up, right? As the x values go up, the y values go up. Right? That's not, okay, that's pretty simple, right? So let's say f is increasing, okay, and let's be very specific. Let's say it's on some interval, right? Because, I mean, usually functions can go up and down and up and down, and when we say it's increasing, we don't mean usually the whole function is increasing the whole time. We just mean some neighborhood, right? It's increasing. So it's increasing on an interval, let's say I, if whenever, say, x1 is less than x2 are elements of I. Okay, so you have 2 points in the interval, x1 and x2, and x2 is bigger. Then f of x1 should be less than, right, f of x2. That's what you were saying, right? As the x values get bigger, the y values get bigger, right? The y values are the output of the function. Okay, that's what it means to increase. Nice. Right? This is another one of those wonderful times in math where, I mean, you look at a picture, you can tell immediately if it's increasing or decreasing. Right? A computer would have a much harder time, wouldn't it? Because it can't just look at the graph and go, ah, increasing or decreasing, right? You have to tell it some rule. How do I know if it's increasing or decreasing, right? Well, I have to give it some rule like this. And of course, it would also have some problems because it doesn't do well with infinite numbers of points. Okay, so that's when it's increasing, right? And what do you think it should be if it's decreasing? F is decreasing if, let's say on an interval, decreasing on our interval I, if, what should it mean to be decreasing? As the x values go up, what should happen to the y values?
They go down.
They should go down. So if whenever x1 is less than x2 is an I, then f of x1 should be greater than f of x2. Okay. That's decreasing. Okay, cool. So now we know what it means for functions to go up or down. Incidentally, you might call this, if you wanted to add a little more subtlety to the definition, you might call this strictly increasing. Right? Because you might have a graph, maybe it looks like this. It goes up, 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 and then it flattens out. And then it goes up, 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 up. Right? So this would not count as being increasing everywhere, right? Because it gets flat. It doesn't grow on these values, right? So you might say that this means strictly increasing, right? And then you could also have one that is just increasing, which allows for it to go up and be constant and then go up some more. Okay, and that would just mean you would put a less than or equal to right here. But we're going to stick with just this definition. Okay, so then here comes the question. How do you know if a function is increasing or decreasing? This definition tells you that you have to look at your interval, take every set of pairs of points, right? Take any 2 points in the interval, and check this condition. Okay, and that's a lot of points to check. Okay. And maybe there's a nicer way to do it. Okay, and well, those of you who have a little bit of pre-knowledge know that the first derivative is somehow going to be involved in this. And that's good because this is a calculus class. We should get some derivatives. To explain how the derivative is going to come into the game here, I first want to just mention something called the mean value theorem. I'm not going to go into great detail into it because we actually have, Shannon, you're doing it, right? Mm-hmm. Yeah, we actually have a final project on it, so you'll get to pick it up a little bit then. And when we start doing antiderivatives and integrals next term, we're going to revisit the mean value theorem and do it in a little more detail. Okay, I just want to give you the idea behind it, just a quick intuition, because we'll want to use it to prove the increasing, decreasing. So the mean value theorem is a very important theorem in calculus, especially if you go on and really do some hardcore analysis. It's extremely important. The applications of it are vast. And usually people are very confused by the statement of it. But I think it's really quite intuitive. Okay? Before we do it, I just want to recall the intermediate value theorem. Right? This is the one that said if I kick the soccer ball into the goal, it has to cross the goal line. Right? That was the one. If you had something which was negative and it became positive and it was continuous, right? It had to what?
Cross the x-axis.
Has to cross the x-axis, right? Has to be 0 at some point. If it was negative and then positive, it had to be 0. Okay, so keep that in mind. Okay, so let's say I have some nice graph, okay, that's representing my position over time. Okay, something's moving, there's my position over time. Okay. And I choose a point, let's call over here, and this would be point A. And how about a point over here? Let's call it B. Here's my question. This is something we've already answered, but maybe you've forgotten. How do I represent, or how do I get the average velocity between A and B?
Relative change in distance.
The relative change of distances. Okay, so what do you mean by that?
He takes a derivative of the...
Remember, I'm doing average rate of change. Over B. Oh, excellent. Okay, so what do? I do f of B minus f of A over B minus A. So let's see. So this, right, there's f of B. There's f of A. There's B. There's A, right? Okay, and so what is this giving me?
Slope.
The slope of, right, the slope of the secant line. Missed. And draw the secant line. Okay. And this secant line has a slope, and that slope is the average velocity between A and B. Okay? So you have this nice expression right here. Okay. Now, let's say I'm going out driving, right? And at the end of the day, I computed that my average velocity was 45 miles per hour. Okay? Now, is it possible that I drove that whole time without ever driving 45 miles an hour? I said my average velocity is 45, but is it possible that I didn't actually drive 45 at any point?
No.
Well, let's see. How could I actually have an average of 45 miles an hour?
You should be going under it and over it, so you'd have to cross it at some point.
Right. Okay, one way is easy. I go 45 miles an hour the whole time. If I go constant, right, that's one way to do it. Of course, then the answer is yes, I went 45. Okay? Or you could go faster at some points and slower at other points. Right? Is it possible to always be slower than 45 miles an hour and get an average of 45 miles an hour?
No.
No, of course not. And is it possible to be always faster than 45 miles an hour and get an average of 45 miles an hour? No. Okay, so the only other way to do it is if I went slower at some point and faster at another. Okay, but if I went slower at some point and faster at another, or faster at this point and slower at another, what did I have to do at some point in between? You had to cross it. Right? It's clear. Okay. That's the mean value theorem. Right? It just says that if you travel at an average velocity, at some point your instantaneous velocity was your average velocity. Okay? So there's some point C, all right, say it's here, where if I draw, well, how do I get the instantaneous velocity rate? That's the slope of the tangent line. Oh, maybe it's probably a little higher up. Okay, there we go. So I have a point here. Well, there's f of c, but I'm not so interested in f of c. Okay. Notice that these lines are parallel, which means they have the same slope, which, of course, slope is representing velocity, right? Okay. So it's saying that the mean value theorem says there is some point in between such that if you draw the tangent line at that point, you get the same slope. Okay? Or, right, of course, the slope of this tangent line is just the derivative at c. Okay. So there is some point c in between a and b, such that the derivative at c is the same as the slope of that secant line. Okay? That's all the mean value theorem says. So it's not that hard. Now there's a few hypotheses you need to put down here for this to make sense, right? For instance, when we use the intermediate value theorem, what was the big hypothesis on the function? What's the key there, right? If I say, oh, I'm negative and then I'm positive, so it must have hit 0.
No, it's continuous.
It had to be continuous, right? If you allow it to jump up and do stuff, right, that's ridiculous, okay? But if it's continuous, no problem, okay? So we used continuity in our argument, right? that if you were going less than 45 miles an hour and you're going more than 45 miles an hour, by continuity you had to hit 45 miles an hour. All right? Okay, so we better assume that our function is continuous on this interval, a, b. Not only that, but we actually need to find derivatives. So it better not just be continuous, it better be differentiable. Okay, so we won't get into it here. There's some technical conditions on, okay, you only need continuity on the open interval AB, but you need differentiability on the closed interval AB. Okay, this is just, hoo-ha for now. Okay, we don't need it. Okay, I just want to call attention to this nice theorem. So we're going to use it to prove the statement about increasing and decreasing. But we probably won't get to prove it until next time. So let me just state it. With the mean value theorem, it's a very easy proof. I mean, this seems, pretty obvious. You could explain this to, a little kid, right? Anybody who knew what an average was, they could understand it. Okay, well, because they don't know what derivative is, but they know instantaneous velocity. That's probably not so hard. Okay, but the applications are going to be pretty far-reaching. Okay, so I'm going to call this the ID test. So, well, we're always going to be assuming now that we have a function which is differentiable on our interval. Okay. So we let f be differentiable on an interval I. So say if f prime of x is greater than 0 for all x in the interval I. So the derivative is positive on that interval, then f is increasing on I. If you have a positive derivative, then the function is increasing. And if the derivative is negative on that interval, then f is decreasing. Okay. Okay, so I want to do a proof of this because at least a third of you said in the evaluations that we did in the middle of the term that you liked the proofs. A third of you said you couldn't care less for them. No. Is that right? Yeah, that's right. You could not care less for them. Good. And then a third said, yeah, I think you do just enough. So I am going to do a proof of that. But let me postpone that until tomorrow. Today, for the last couple minutes, let's just do an example. Right? So let's just write down some easy fourth degree polynomial. Okay, so this is pretty nasty looking, right? Who knows what the graph of that is? We don't now, but you will soon. Let's try to figure out where it's increasing or decreasing. Okay. To do that, well, take derivatives. All right, tell me the derivative of this.
12x3.
So I need to solve this for 0. Ooh. Okay, well, there's something good happening here, right? There's an x in every term. So, and, well, I can probably factor out 2, right? So this is 2x times, all right, I get 6x squared plus 3x minus 4. Okay, now how do you use this? Well, I want to see where it's positive and where it's negative. Okay? A good way to do that is to actually figure out where it's 0. Right? Because you know when it's 0, well then on one side it had to be positive and on one side it had to be negative. Okay, so let's figure out where it's 0. So let's see, let's set f prime of x equals to 0. Then, well, let's see. This is one way you could get a 0 out of it, right? If x was equal to 0. Okay. Or, well, now you have to figure out if does this thing factor, or what's a quick way just to do it is use the quadratic form, right? So x equals, let's see, minus 3 plus or minus square root of 9 minus 4 times minus 4 times 6. So that's 16 times 6, which is
96.
good. And plus, right? Because we have a minus there. Okay, over 12. Okay, and of course you could simplify this a little bit, not much. Square root of 102.
Which means 105.
Yes, thank you. Okay, which unfortunately, this is a product of 3 distinct primes. 3 times 5 times 7. So you're not going to be able to pull any squares out of it. So that's just what it is. That's good. Okay. Fine. Okay, so but here are our 3 roots. Okay, now here's what you do. You draw a little line. And you try to put your 3 roots onto the line. So one of them is easy. There's your 0. Now what about these? Well, let's see. Minus 3 plus, okay, well, this is a little bigger than 100, right? The square root of 100 is 10. So this is a little bigger than minus 3 plus 10, which is 7 over 12. So 7 twelfths, a little bigger than a half. Okay, so if there's a half, so let me call the 2 roots alpha and beta. Alpha is the plus and beta is the minus. So alpha would be right about there. Okay? There's alpha. Okay, and beta, well, that's minus 3 minus a little more than 10. So it's minus 13 over 12, so it's about minus 1. So there's minus 1. So beta can be over here. Okay, and now you just plug in values, right, into the derivative at these places to see what you get. Okay? Now, you don't have to put in anything right near beta. You can put in something really, really small, like minus 100. You put in minus 100 here, you're going to get, okay, positive 600. Right? Oh, I'm sorry, excuse me. Minus 100, you get 100 squared, right? It's really, really big. These things aren't going to matter. So it's going to be positive, and then a negative. So it's going to be negative. And then in between, well, let's see, let's put in minus 1. You get 6, minus 3 is 3, minus 4 is minus 1, times minus 2. That's positive. Okay? Then, well, you can put it in a half, and then it's going to be, let's see, well, that's going to be positive. Okay, a half, that's a fourth, 6 fourths plus 3 halves minus 4. Ooh. 6 fourths plus 3 halves. That's what, 12, 24 over 8, that's 3. Minus 4 is going to give you negative. Then you put it in big numbers, like 100. You get positive, positive, subtract 4, doesn't matter, times positive. Okay? And so now we know exactly where this function is increasing and decreasing. So we're going to get a lot of practice doing this. Okay, so tomorrow we'll prove this ID test, and we'll get into the first derivative test and beyond.